Right, in this session, we're going to have a look over a few basics around complexes, how they form, how they are named. We're not going to deal with isomerism of complexes within this video. I will follow up with a short video looking at different forms of isomerism after this one, but this one mainly looking at just covering the basics. Okay, so first of all, formation of complexes. What is a transition metal complex? How does it Okay, so this type of species is where you have a central transition metal ion surrounded by species called ligands. These are bonded to that central transition metal ion through a dative covalent bond, but in this context, this type of bond is usually referred to as a coordinate bond. The complexes themselves, depending on the charge of the transition metal ion and the charge of the ligands, could be positively charged overall, in which case we call it a cationic complex. They could be negatively charged overall, in which case they're an anionic complex, or they could be uncharged. They could be a neutral complex. Now, these complexes can form due to two main reasons. First of all, there's the idea of transition metal ions being quite small and therefore very charge dense. Their positive charge is not spread out over a very large volume. This means that when placed in the presence of species with lone pairs, they can strongly attract those lone pairs towards themselves, so strongly, in fact, that it actually forms a covalent bond, your dative covalent bond. Now, you can think a little bit, if you think back, this might sound a little bit like what you have discussed within the thermodynamics topic, looking at data from Born-Haber cycles. If you remember, certain certain ionic compounds have a large difference between their theoretical lattice energy and their actual lattice energy, because as well as the ionic bonding, they also have a degree of covalent bonding. And this happens when you've got a very, very small, very, very charge dense cation that is able to pull the electron density of the anions back towards themselves. This is very similar to what's going on here, where the transition metal ions are pulling the electrons in a ligand towards themselves to form a dative covalent bond. The second reason why these complexes are able to form very effectively is because of the vacant d orbitals present in your transition metal ion, which give them space to essentially accommodate electrons being donated towards them in a coordinate bond. Okay, last thing to note at this stage is that the number of coordinate bonds around a central transition metal ion is referred to as the coordinate number of that complex. Doesn't refer to the number of ligands, it refers to the number of coordinate bonds. Important to get that distinct. So you could have a complex with 4 ligands in it, but if there are 6 dative covalent bonds, then the coordinate number is 6, not 4. Okay, so moving on to the next bit. So shapes of complexes. Here we have a hydrated complex of copper 2+, by which we mean that we've got ligands which are water molecules, each donating a lone pair towards the central copper. Water is a neutral ligand, and so we can tell in this complex that the copper must be Cu2+, so we have an overall 2+ charge. This is a cationic complex, and it has a coordinate number of 6. Okay. Note in this case the way that the complex is drawn out. The, as it were, vertical coordinate bonds within the complex are shown as being within the plane of the paper. They're just drawn with lines. Even though these are coordinate bonds as well, even though these are dative covalent bonds, we do not draw them as arrows when we're drawing out the complex. It's just understood that these are coordinate bonds. You don't need to use the symbol. The other 4 bonds, you've got 2 bonds going away from you into the screen. These are signified by dashed bonds, and you've got 2 bonds coming towards you, which are signified by wedges. This is always how you draw your octahedral complex. Okay, the next type of complex is a tetrahedral complex. In this case, we've got copper surrounded by chloride ions. Chloride ions are Cl minus, of course, 1 minus charge, and this complex is overall a 2 minus charge. So actually the copper in this complex is still 2 plus. However, we have an anionic complex because the overall charge is negative. When you've got 4 negatives and 2 positive, the overall is 2 minus charge. The coordinate number of any tetrahedral complex is 4. You have 4 dative covalent bonds. Okay. The last shape that you need to know about for your A level is a square planar complex. Now, if we have a look at this particular example here, we've got platinum in the middle. We don't know what the charge of that is as yet, but we know we've got 2 ammonia ligands, which are neutral ligands, and we've got 2 chloride ligands, which are negative. The overall charge of this is 0, so we got a neutral complex here. And that means that the negative charges of the chlorides must be cancelling out with the positive charge of the platinum. If we've got 2 minus 1 chlorides, the platinum is 2 plus here. Now, with this particular complex, if you've got a square planar complex, the coordinate number is again 4. Now, at A level, you don't need to spend a lot of time thinking about why you would get a tetrahedral or a square planar complex. There are a couple of examples that you need to be aware of, these 2 on the page. There's a little bit of an explanation you can give at this level, a bit of a simplification, but it works in terms of explaining this, and that's to think a little bit about electron pair repulsion theory. If you have a look at the bond angles within these complexes, you will note that the square planar complex has a smaller bond angle, and so crowding around that central ion is going to be more of an issue. So essentially, if you have a combination of central cation and ligands that's going to lead to more crowding around that central cation, in order to minimize electron pair repulsion in the complex, you will go for a tetrahedral species. So if the transition metal ion is particularly small, so towards the top of the D block, and the ligands are relatively large in size compared to that central transition metal ion, you will go for a tetrahedral shape in order to minimize electron pair repulsion. And this is what is happening in this copper chloride complex. However, if your transition metal ion comes from further down in the D block, so such as platinum, then repulsion of the electrons of the ligands in the complex is less of an issue because you've got a larger central ion, so they are by necessity more spread out. And in this case, square planar becomes preferred. The reason for the preference of the square planar complex is to do with electron configuration in the complex, but we don't look into that much depth at the A level, so you don't need to worry about it. But essentially, if there's less crowding around the central ion because the central ion is large and the ligands are smaller, then you will prefer square planar in a lot of cases. Right. Basic naming rules for complexes then. So when we have species being used as ligands, in the name of the complex, they're coded by words that are not the same as the name for the ligand when it is not acting as a ligand. So for example, H2O on its own is of course referred to as water, but when it's within a complex, we indicate it by the prefix of aqua. NH3 on its own is ammonia, but when we're naming it within a complex, it's amine. And note here, it is a double M, which distinguishes it from amines, the organic compounds, which can actually also act as ligands. So be careful on that one. OH minus acting as a ligand is hydroxo, Cl minus acting as a ligand is chloro, and F minus is fluoro, and Cn minus is cyano. Now, if you have a complex which has got a mixture of these ligands, the ligand prefixes are always organized alphabetically. So cyano would always come before hydroxo, but after chloro, for example. Now, of course, we can have different numbers of the ligands as well, so you also need prefixes added to indicate the number of ligands of that type. Now, the numerical prefixes do not have any effect on the ordering of the prefixes for the ligands. Okay, so we'll have a look at how these rules play out. So let's go back to our examples here. So for this first one, we've got 6 water ligands. So we would have hexa, aqua. Note here we do have 2 A's in a row, 1A from the hexa and 1A from the aqua. And then this is going to be copper, because we've got copper in the middle, 2, because it's copper in the 2+ oxidation state. So hexa, aqua, copper 2 complex. The last ion that we have on the page here, if we were going to name this systematically, so we've got 2 ammonia ligands, so those are going to be amine, and we've got 2 chloride ligands, so those are going to be chloro. So we're going to have diamine, dichloro, platinum, and then again we indicate the oxidation state of the transition metal with a Roman numeral. Diamine, dichloroplatinum 2. Okay, right. Now, what about this one here? Well, for this complex, we need to discuss an additional rule, which is specifically in the case for anionic complexes. Now, anionic complexes can act as the anion within an ionic compound overall, and as such they need to be named similarly to how anions would be named. Now, what goes on with an anionic complex is that the transition metal part of the name is altered to end in ATE. And in addition to this, that you are often switch to a Latin form of the name. Now, how do you know when you're going to need to switch to the Latin form of the name? A good indication would be, is the symbol of the the element in question different from its English name would suggest. If so, that's probably because the symbol is derived from the Latin name, therefore it has a Latin name and you should switch to it. So let's have a look at how some names might change. So we could have, for example, cobalt would be converted into cobaltate. Zinc would be converted into zincate. And let's think of another one. Manganese would be converted into manganate. Now, what if, though, you had a complex that looked like this? Well, in this case, because we've got gold, and you can see from the symbol for gold that the symbol is not derived from an English name, it's derived from a Latin name. So let's put together the name for this complex. We're going to have dicyano, and then instead of doing goldate, we would use aurate from the Latin aurum. If we had this complex, in this case, we've got 6 cyanoligands, so we would have hexa, cyano, and again, iron, its symbol is derived from the Latin name, so we switch to the Latin form of the name here. And here we actually have to, and I've got the charge wrong, that should be 3 minus. Here we actually have to determine the charge of the transition metal ion itself. So ionides are each 1 minus. So if we've got 3 minus overall, the ion is 3 plus. So it's hexacyanoferrate 3. In this case, the gold has an oxidation state of 0, so we don't put an oxidation number after it in its name. Right. So that said, let's go back and have a look at this tetrahedral complex now. Here we've got 4 chloride ligands, so we're going to have tetrachloro. But copper, again, is one of these elements that has a Latin name, so we're going to go to tetrachlorocuprate. And copper's in the 2 plus oxidation state, so tetrachlorocuprate 2 is the name of this complex. Okay, so next thing that we have to deal with is the issue of bidentate and multidentate ligands. So these are ligands that form more than one coordinate bond to the same transition metal ion. They're sometimes also known as polydentate as well as multidentate. The word dentate relates to the Latin word for tooth because when you've got these multidentate ligands, they kind of look like they're biting down on the central ion. In order for a ligand to act as a multidentate ligand, you need to have more than one atom with a lone pair within the ligand, and depending on how many suitable atoms you have within the ligand, you will alter the denticity of the ligand, as in how many coordinate bonds it can form to that central ion. Okay, and depending on the denticity, you've got different names for the types of ligand you'd have. So bidentate means it's got a denticity of 2, tridentate has a denticity of 3, tetradentate 4, pentadentate 5, and hexadentate 6. Let's just get rid of those. Okay. The last thing to say about multidentate ligands is because they bond multiple times to the same ion, they have a higher affinity for bonding to transition metal ions to form complexes than monodentate ligands will. And so they will tend to displace monodentate ligands and completely encapsulate your transition metal ion. This effect is known as chelation, or the chelate effect, which comes from the Greek word for claw, because these multidentate ligands, when they bind to a transition metal atom, they kind of look like claws holding around that ion in the middle. Right, now the question that we have is, how do we identify something as a multidentate ligand? Well, the first requirement, as mentioned previously, is that there must be more than one atom available with a lone pair within its structure. But this is not the only thing that we have to think about. And in order to draw out this idea a little bit better, let's have a look at an example of a potential ligand. So if I draw out this structure here for you, this is ethane dioate, which is a conjugate base of a dicarboxylic acid. And in this structure, we actually have 4 atoms with available lone pairs, which can be used for bonding to a central transition metal ion. Now, you might think, oh, well, surely that means that this is going to be a tetradentate ligand. Simple enough. 4 atoms available with lone pairs, therefore 4 coordinate bonds can form. What we need to do, though, is to think, can those lone pairs all bond to the same transition metal ion at once? And this is a different question. So let's have a look at some different pairs of atoms being used here. So let's, for the first example, look at these 2 atoms here being used for bonding. So if we got M as our transition metal ion, we can form a bond to one oxygen up here and a bond to another oxygen here. And then what we end up with is a structure that looks like that. What we formed here is a ring with the ligand being bridged over by the transition metal ion. And in this case, we've got a 5-membered ring. 1, 2, 3, 4, 5 atoms within the ring. Now you can see here that the other oxygens are far too far away from the metal ion in order to actually bond to it, and therefore they do not take part in the complex. So we've got this ligand acting as a bidentate ligand here, not a tetradentate ligand, because the other oxygen atoms just can't be brought in close enough to the metal ion in order to form a bond to it. And if they did, the bonds that were formed would be far too close together and would therefore have a prohibitive amount of electron pair repulsion, which would mean it would be unstable and would break down. Okay, now if you've been looking carefully at the complex, you might note that there is another pair of atoms that could be used at the same time to form a transition to form a complex with a transition metal. So let's have a look at these two being used at once. Now in this case, we've again got our metal bonded to the two oxygen atoms, but these are bridged only by one carbon in between them. So that would be what our complex would look like. Now, you can see straight away the difference here. Here, rather than having a 5-membered ring, we've got a 4-membered ring. Now, why is this important? Well, it's important to consider because of the bond angles. If you've got a 5-membered ring, you are essentially forming a pentagon out of bonds, which gives you a bond angle of 108 degrees. Whereas if you've got a 4-membered ring, you've only got an angle of 90 degrees. So there is more electron pair repulsion here. And this makes the complex unstable. 4-membered rings do not happen. 5-membered rings are pretty much ideal. You've got enough space between the bond pairs to minimize electron pair repulsion. 4-membered rings, not so much. So when you're looking at, for example, a carboxylic acid, C double bond O, and it becoming deprotonated to give you O minus, so a carboxylate rather. While your carboxylate functional group does have 2 oxygens with a lone pair on each of with lone pairs on each of them, it does not act as a bidentate ligand, because in order for both of those oxygens to form dative bonds to the same transition metal ion, you would end up with a 4-membered ring, which is unstable because the bonds are too close together and there's too much repulsion. Now, there is an exception to this, and that's the case of a chromium to ethanoate complex, which actually usually forms within solution with some water aqua ligands on either side as well, so that each chromium has 6 bonds around it. Now in this case though, it's important to note that the carboxylate, the ethanoate ligand, the oxygens in this ligand are not both bonding to the same chromium. You've got one oxygen bonded to one chromium and another oxygen bonded to a second chromium. So you can see that the ring that is actually formed here is much wider and therefore has less electron repulsion. The ethanoate ions are not acting in a typical bidentate manner because they're not both bonded to the same chromium atom. Okay, so this is a particularly interesting complex because it involves two chromium ions rather than just one, and they're held in a complex together by being bridged by these 4 ethanoate ions that are coming in at 90 degrees to each other. Another interesting thing about this complex is it actually has a quadruple covalent bond between the 2 chromiums. This was one of the first quadruple bonds that was ever discovered, but again, this is chemistry that we don't particularly look into at the A level. Right, the very last thing to have a look at is how do we name complexes with more complicated ligands in them. Now, there's a variation in the prefixes that are used to indicate the number of the type of ligand, and the reason for this is just to avoid ambiguity. Because the name of your more complicated ligand, your multidentate ligand, is going to be a more complicated name, obviously avoiding ambiguity is going to be important. So Instead of using the di prefix to indicate two such ligands, we use bis. Instead of tri, we use tris. Instead of four, tetra, we use tetrakis. And instead of penta, we use pentakis. Okay, so let's have a look at naming a particular complex then. So if I had, let's use let's use this ligand here. So this is 1,2-diaminoethane. And you can already begin to see why it's going to be important to avoid ambiguity here, because the name of this ligand has a di in it. We don't want the di indicating the number of ligands to become confused with the di indicating the number of amino groups within one ligand. Okay, so let's have a look at a suitable complex that we might have here. So let's go for a nice octahedral complex of nickel. I'm going to say that this is going to be Ni2+ in the center. And because this is octahedral, we've got a coordinate number of 6. So we would need 3 bidentate ligands. And we know that this can act as a bidentate ligand because the nitrogens have lone pairs on them. They are separated by 2 carbon atoms. So if both of these were to form a dative bond at once to the same transition metal ion, we've got a 5-membered ring. So that is fine. Now what I'm going to do, and these should be NH2 rather than NH3. Do not make that mistake. Right, so what I'm going to do is I'm going to draw on all of my NH2 groups without drawing the rest of the ligand just to start off with. It just happens that this is the easiest way to go about doing this. Also, do make sure that you reverse any ligand groups so that the atom with the lone pair is the one that is forming the coordinate bond. That is quite important. Right. Now these groups are connected up by a carbon chain, and these carbon chains I'm going to add in now in skeletal formula format. So like that, and just make sure that it's clear that it's a 2-carbon chain there. Now as each of these ligands is uncharged, this will overall have a 2+ charge if we've got nickel 2 involved. Now, how do we name this? Well, we've got 3 lots of the 1,2-diaminoethane ligands, so this is going to be tris 1,2-diaminoethane nickel 2. Okay. Right. Now, to finish up with the most complex example that you will be expected to know about, and that is a ligand derived from this lovely molecule here, which is known as ethylene diamine tetraacetic acid. Now this is abbreviated to EDTA, and because it's such a mouthful, we pretty much only ever use the abbreviation of EDTA. Now, this particular molecule here is, as the name suggests, it's got 4 carboxylic acid functional groups, and each of these can be deprotonated. So we end up with a structure that looks like this. And we can see here that we have, well, we've already identified the fact that typically carboxylic acids, carboxylate functional groups only act as monodentate ligands. So you've got 1, 2 atoms here that are available with lone pairs, 3, 4, 5, and 6 potential atoms for bonding here. Now, that means that potentially this could act as a hexadentate ligand, but we just need to check that we would form rings of the right size here. So between this atom and this atom, if both of these bonded to the same transition metal ion here, the metal ion would be one atom, 2, 3, 4, 5. 5-membered ring, that's fine. Okay, and that would be the same for this one. 1, 2, 3, 4, and then the transition metal ion 5 in the 5-membered ring here. What about between the nitrogens? So if we had a transition metal ion bonded here, so that would be 1, 2, 3, 4, 5. So that's fine. And the distances are the same on those sides as well. So you get 5-membered rings here. So this is a hexadentate ligand. Now, this means that what we refer to as EDTA 4 minus is a very powerful chelating agent and is pretty much able to replace any other ligands on a transition metal complex. It forms a cage completely encapsulating the central transition metal ion. Fortunately for you, you will not need to name EDTA complexes. You will just need to write out the formula, but even then, you will be writing the formula in the representation of just EDTA as the form of that ligand, rather than writing out the molecular formula of that, which is rather long.